thank you for coming out to the doctoral dissertation defense for Jana Pavlasek. Jana joined us in 2018, coming from McGill University, where she'd already been an accomplished roboticist working on many different projects. She has thrived here at Michigan, putting together a great publication record, but also providing mentorship to many students who follow her leadership on many great projects. But this project, this dissertation is really, I think, a very different type of dissertation in that it both balances the teaching and research. So providing that balance between the things that we do for not just creating new ideas, but also helping to educate people on those ideas and help them extend it in new ways. And so this I think is a potentially transformative dissertation. And I can't think of somebody who is more emblematic of the current academic culture in Michigan robotics. And so with that, I will pass the floor to Jana.
Great, thank you, Chad. All right, well, hi everybody. Thank you so much for coming. So today I'm going to I want to talk to you about the work that I've been doing while I've been here at the University of Michigan on distributed inference for robotic perception and planning under uncertainty. But before I get to that, I want to kind of go back in time a little and tell you about how I got here. So this is my first robot. I went to McGill University in my first year of undergrad. I joined this design team where we built autonomous underwater vehicles. We went to this competition in beautiful San Diego. So this is me in my very first year at this competition after my first summer of undergrad in 2014. And I learned a whole lot in doing this project. One of the big things I learned is that underwater robots are really hard. So there's no communication with an underwater robot. There's no Wi-Fi. And there's very limited visibility, like you can see here. There aren't that many. There's only a few sensors that work well underwater, and they're very noisy. And then, of course, the extra fun challenge of all your expensive electronics being underwater. So this is me again, having graduated to being in charge of the software of the competition in my last year. But I loved this experience. I had a great time, and I thought it started to make me think that maybe I could do robotics as a career. And so I was thrilled to get my first, to get an internship at ClearPath Robotics in their auto motors division. And they build these big robots that are like autonomous vehicles for factories to like move pallets around. And coming from my background of underwater robots, I was kind of thinking, this thing doesn't even go underwater. What's so hard about that? But there's a bunch of people with PhDs working on these problems, so obviously there must be something there. And it turns out that we still have the challenges of having to deal with this uncertain sensor data, but unlike the underwater case, this is a challenging environment because it's very dynamic. There's people moving around, there's other robots that we have to interact with. So it turns out that this is a very challenging and unsolved problem, and it really motivated me to look into doing a PhD in robotics. And I was really excited to join my lab here at Michigan. My lab mates actually did this demo for me in my visit day when I came to visit Michigan. And I was excited to work on these problems in these very unstructured environments. There's no green screens, no nicely separated objects, but these challenging, cluttered environments that we need to be robust in. And there's a lot of different diverse scenes and solutions that a robot has to encounter and consider in order to be able to operate in these conditions. So I've been lucky to work on a variety of different interesting problems in my career so far in robotics and industrial robotics, field robotics, and assistive robotics. And it turns out there's a lot of interesting shared challenges between all of these problems. And I have one last box here, which is another thing that I learned is that if we want a chance to deal with to solve these challenging problems, we are going to need to train up a diverse pool of talented roboticists to help us do that. So robotics education is another problem that I've also got to do a little bit of work on in my PhD that I'll talk a little bit about at the end. So to dig in a little more to this problem of assistive robotics, a robot needs if you want a robot like this one, this is the robot that we have in our lab here at Michigan, to be able to do tasks like some assembly and maintenance tasks, manipulating different objects in an office or a home environment, we first need to be able to actually perceive the objects. And we can't just have, like a 2D bounding box around the object or something like that. We need the information that's precise enough for an actual robot to manipulate it in 3D space. And that can be really hard if we have environments like this one where there's occlusions on the object, around the objects, making them hard to see. And if you have objects that have a complex structure, like these ones are articulated so the parts can move with respect to each other, so that adds degrees of freedom to the problem. And if we can actually perceive these, if we can, localize these objects properly, then we have to make plans to be able to manipulate them. And that in itself is challenging because there's lots of different ways to manipulate an object. It might depend on how you grasp it and which way you go around obstacles. It's a really challenging solution space to deal with. And you have to deal with these dynamic scenes with lots of different robots and different agents around. And of course, these problems feed off of each other, making the overall challenge of robotics very difficult. So my work asks how we can have robots operate reliably in these types of unstructured and dynamic environments. And the point that I'm going to try to make is that in order to do this, we need good models of uncertainty. And so a question that I like to think about when I think about this problem is, what is the best inductive bias for robotics? And when I say inductive bias, I like to use this example to explain it. So these are two models of the Earth, of the solar system. One is with the planets revolving around the sun, one is with the planets revolving around the Earth. And these are actually both correct models. They're both like mathematically equivalent models that match the data. But this model that we have of all the planets revolving around the sun is a lot more descriptive, a lot more helpful for us to advance our understanding of this area. So it's really important what actual models we are choosing to use. So in my work, there's two of these models or inductive biases in my thesis that are connect all of my different work in this area. So the first is that we want to represent the distributions of possible solutions. And particularly, we use something called the non-parametric distribution that I'll talk a little bit about later for modeling problems like the uncertainty around the pose of an object or a trajectory the robot might take, with the idea being that if we want to solve complex problems, we need to model diverse solutions to these problems. And the other one is that these are really complicated, high-dimensional problems. So maybe instead of solving one big complicated problem, we can solve lots of smaller problems in parallel, like estimating an object in terms of its parts or decentralized control for robot swarm systems. And we can solve all the subproblems by passing messages between communicating entities. So I've been talking about these problems in robotics that are high-dimensional, have multiple possible solutions. It turns out another problem like this is actually the problem of robotics education. So I've been lucky to get to work on developing a new class as part of Michigan's undergraduate robotics curriculum. And we've also been able to draw some of the same ideas from the rest of this dissertation. Specifically, we've been looking at a model called distributed education, where we're able to collaborate with different institutions to kind of distribute resources in order to create more robotics classes at more institutions. So I've been lucky to get to work on a lot of interesting projects while I've been here at Michigan. My dissertation talks about 4 of these. My work, and they encompass my work on perception and planning for robotics, and also my work in teaching an introductory robotics class. But today I'm going to focus on just 3 of these for the sake of time. So I'm going to start off talking about my work on articulated pose estimation, and then my work on multi-robot coordination, and then I'll talk a bit about the teaching project. Okay, so objective of this work was that we wanted to be able to recognize and localize the pose of an object so that the robot could do some sort of manipulation task using that object. And our main insight in this chapter is that distributed inference lets us do tractable and robust pose estimation, especially in these challenging environments like with heavy clutter. And so the goal is that we want to use the robot's sensor information, the robot's RGB and depth observation, in order to localize the pose of the object. So the pose is the 3D position and the 3D orientation. So it's 6-degree of freedom pose. And so there's been a lot of work in this pose estimation domain. Generally, if we look at rigid body pose estimations, just of one rigid object, there's a breadth of different probabilistic methods, as well as learning-based approaches, which have become growingly more popular in recent years. And there's also been this kind of growing interest in these hybrid methods that draw on both probabilistic methods and learning methods. But these tend to deal with rigid body pose estimation, and we're interested in these hand tool objects, which might have articulations in them. And so there's also a number of different works on articulated pose estimation to identify the interactions, the articulations themselves based on interactions, as well as some learning and probabilistic-based articulation methods. And they tend to deal with kind of these bigger objects that are easy to detect, right, like cabinets or things like that, and mostly in the depth image. And we're kind of interested in these more fine, detailed tool parts. And so our insight in this project, in this problem, was that we could apply distributed inference to do parts-based pose estimation. And the way that we did that was to represent the object in terms of its component parts in a graph. And if you have this undirected graphical model, that's called a Markov random field. So you can represent this probabilistically so that you can get a belief over your object pose. And so each node represents the pose of one of the parts of the object, and edges represent geometric relationships between those parts. And if you have a graph like this, the kind of interesting thing about it is that you can decompose it into this product of much simpler factors. So the final belief over the whole object pose is a product of these two potentials. The first is the pairwise potential, which tells us how compatible a pose is with a neighboring pose and a neighboring part in the graph. And the next one is the unary potential, which tells us how compatible an estimate is with our observation. Another insight we had is that we wanted to be able to incorporate both data-driven techniques and probabilistic inference so that we could leverage the strength of both. So our pairwise potential lets us leverage these known prior geometric relationships that we can express about the objects. And then our unary potential uses a convolutional neural network that lets us do fast estimation, and we don't have to hard code any complex likelihoods. And then we use an algorithm called belief propagation, which lets us maintain belief over our object pose and be robust in difficult environments. So our unary potential looks something like this. If we look at this example of the clamp handle here, we pass it through a neural network that we train to give us this heat map over the robot observation. And then we formulate that as a probabilistic factor within the probabilistic framework. And we do that by basically quantifying how well our pose estimate corresponds to this heat map. So if it overlaps really nicely with the heat map, then it'll get a high score, a high likelihood score. And if it doesn't, then it gets a lower score. And our pairwise potential represents just the geometric compatibility of two pose hypotheses for neighboring parts. So if we look at our clamp again, and we take a look at the clamp bar and the clamp handle, this is an incompatible pose, an incompatible configuration because those parts are overlapping. And if we have compatible configurations, we'll get top scores, and as the poses are incompatible, they'll get penalized. And so we can combine these two potentials together using this algorithm called belief propagation that I'll go over briefly here so that because it comes up again later in other chapters as well. And so we want to represent the pose of a part. If we take the clamp bar, for example, it's going to be a product of the unary potential, so it's observation potential, and then these incoming messages from the neighbors. And so the incoming neighbors messages is the kind of trick of belief propagation, and those are just defined as a product of the pairwise potential with that neighbor, and then also that neighbor's own unary potential. And then it recurses through the graph, so it's also a product of any messages that might be coming in from that node's neighbor, so information gets propagated through the whole graph. So that's how we can kind of combine these simpler potentials into belief of the object part, but we haven't talked so much about what this belief, how to actually represent this belief, how to represent this uncertainty over where our object might be. So how do we represent this? Well, one way that we might think of is to just take some estimate of our object. Maybe if I'm looking at this set of pliers, I might have this guess, and I might just put some covariance around it and use that to represent how sure I am about that guess. And that's our familiar Gaussian model. But does that actually give us a good enough representation of the belief over our object? Well, the pliers that I picked actually are symmetric, so you should probably represent that you have probably even probability about whether it's in either of the two symmetric configurations. And if we actually look at what a neural network might tell us about this image, there's another set of pliers in the back, so you maybe want to represent that there might be some likelihood that the pliers might be located at that other configuration. So you get this complex likelihood that function that looks something like this. And this is just a 1D representation. It looks much more complex in 6 degrees of freedom. And so this is a distribution that's really hard to represent parametrically. It's no longer just a nice bell curve. And so what we do is we represent it non-parametrically, by which we mean that we represent the belief by samples from the belief. So that basically is just the belief is approximated by some possible poses that the object might be in. And so we take that approach to solving this problem, and we use our learned likelihood by passing our robot observation through this convolutional neural network, and then we can combine that with our geometric model in order to represent the likelihood of a bunch of different particles over our object, and we can draw a pose estimate from there. So this is a nice separated example. We were really interested in how this would work in cluttered scenes where some or all of certain parts of the object are occluded. And so we were able to get robust pose estimation by combining these different sources of information in these cluttered cases in this data set that we created as well. So we were able to use this distributed inference approach to give us this tractable and robust pose estimation. We showed that it worked particularly well if the environment was cluttered. And so we had this was actually the first project I worked on in my PhD, so we've done a few interesting things since then. I collaborated with my lab mate Stanley to look at how we could learn the likelihood using implicit models to kind of lower the amount of information that the user had to give about the objects. And I also collaborated with some lab mates about how we could make models to actually manipulate the objects based on this parts-based representation. But one thing that I was really interested in was this kind of distributed inference approach and how we were able to use that to scalably model this problem, and we started to think about whether we could apply the same ideas across different problems. So, and we started thinking about the problem of multi-robot coordination, and it turns out that we can model it the same way and use a lot of similar approaches and ideas for that problem as well. So that brings me to the second part of my talk about multi-robot coordination. So in this project, our main insight was that if we could model diverse solutions to our multi-robot task, we could get this robust and adaptable planning in multi-robot environments. So if you want to solve a multi-robot, if you want to do multi-robot control, one way to do it is you can do it centralized, which means that you can have just one computer that communicates with all the robots, and you find a path for all of them at the same time as one big problem. So this only works if you have full communication with all of your robots, so it doesn't work super well if you have a limited communication environment. And it also gets harder and harder the more robots you have. The problem gets higher and higher dimensional. So the other way of looking at it is to do decentralized control, where each agent has its own controller, and it selects the best action based on local information from its neighbors. So this will scale better to large swarms, and it also factors the problem into lots of smaller ones, which is our nice feature of distributed inference. So we wanted to work on this approach, but one of the problems that we have with decentralized control is that it's very prone to this situation called deadlock. So you can think of these little triangles as little simulated robots trying to just cross to the other side of this environment. And this is one of the kind of classic approaches to this problem. And you can see if you just ask the robots to not get just a little bit too close to each other, they get into this deadlock case, which you could think of as like when you're walking down the hall and you're like kind of going back and forth, you can't decide which way to go when you see someone coming towards you. So that's called deadlock. And these types of conditions come up a lot in these algorithms. So we introduced this method called sign variational belief propagation and used it for multi-robot control. And we're able to get smoother trajectories that are better able to avoid these types of conditions. So I'll tell you how we were able to do that. Our other insight was that we could model this problem probabilistically, and that would let us consider the uncertainty over what action the neighbor might select. So again, we can model this as a Markov random field, like in the articulated object problem, where nodes represent one of the robot's trajectories, and edges represent which robots are in communication range. And then we can use belief propagation to pass messages through the whole graph. So in that way, it looks the same as our parts-based pose estimation problem from before. So to describe how we represent this planning problem as an inference problem, I'm going to go back to a single robot example, where kind of classically, if you want to plan a trajectory for a robot, you would try to find the best trajectory to get from your start to your goal. If you planning as inference is a formulation where instead you want to represent a distribution of possible trajectories that the robot might take in order to get to its goal. So this often, if we have obstacles or other in our environment or other challenging conditions, then we get multiple different modes in our trajectory. So you go one way or another way around an obstacle, for example. So we can use a non-parametric distribution, which will let us represent these diverse solutions by representing a set of possible trajectories the robot might take. And so the kind of classic approach to doing this, to inferring this non-parametric distribution would be to use a sampling-based method. But sampling-based methods tend to be prone to mode collapse, even though in theory they can represent arbitrarily, or they can represent multimodal distributions. In practice, most of the time it's hard to get them to not collapse to one single mode. This is one of a common sampling-based trajectory solver algorithm. So we got interested in this method called sign variational inference, where we can model a distribution in terms of particles non-parametrically, and then it iteratively updates these particles using this update rule. And the update rule is a function of our some likelihood of our particle and also a kernel over our particle. And that kernel acts intuitively, it acts as a repulsive force between particles. So Stein VI is very good at maintaining modes and distributions because of this repulsive force and tends to not collapse compared to sampling distributions, sampling methods. So Stein variational inference has been applied to the problem of multi-robot control before and we extended this work in planning with Stein variational inference to planning to goal sets where there's some uncertainty over the goal region. And this is another chapter of my dissertation that I'm not talking about today, but you can read it if you want. I don't know if I was gonna do that. Yeah, so it's the Stein variational inference is really interesting because it ends up giving you these really cool results where you get these nice multimodal distributions that you just don't get with without applying a whole bunch of tricks to sampling-based methods. This is a cool result, but I've only been talking about this in terms of planning for one single robot. And I said at the beginning that I wanted to plan for multiple robots in this kind of graph inference problem. And so we applied we extended Stein variational inference to apply it to graphical planning over, to problems of probabilistic inference over graphs by using this algorithm that we proposed called Stein variational belief propagation, which is a message passing framework that uses Stein as a solver. So this is our little toy example to kind of show a bit how it works. You can think of each of these little colored dots as a different robot, and the robot gets a signal, which is a distance to another robot. And then it also has some observation of its environment, which I've just kind of represented as a mixture of Gaussians here. And so we get, if we solve that problem and we apply Stein variational belief propagation, we get this nice multimodal result. And that actually lets us, when we have higher noise situations compared to particle belief propagation that uses sampling-based methods, it will kind of collapse to local minima very easily, just if you apply it out of the box, whereas ours applied out of the box does a better job of representing multiple different modes of the solution, which is going to make it more likely to have a good solution in that belief. And so we actually get lower error compared to sampling-based methods. We can also, because of this repulsive force, it is also more particle efficient. So it can use less particles, even if we use just a pretty small number of particles, it achieves pretty low error, whereas sampling-based methods will need a lot more particles in order to do the same thing. So we wanted to apply it to this multi-robot problem. We did a multi-robot iterative finite horizon trajectory problem where we represented the nodes as robot trajectories, and they have a unary potential. When we pick our unary potential, it corresponds to whatever our cost is. So, you know, the energy expended, the energy that the robot uses, and the avoiding collisions with obstacles, and however you want to code it up. And the pairwise potential will encourage robots to stay within a certain radius apart from each other and not collide. And then the robots pass messages between each other in order to perform inference, which lets information propagate through the whole graph. So if we look at how this works back in our little robot environments, we can get these cool looking solutions where if you look especially at the beginning of these little videos, they'll play again. You see these nice splits between when the robots are not sure what the best choice to take is, and that lets us have these really smooth, nice behaviors. And if we compare it to our common baselines, it does better at avoiding deadlock, and it can be much smoother and quicker to achieve its goal than these baselines. But another thing we were really interested in is whether how this would work on a real robot. That's always our question as roboticists. So we use these little robots that we actually use for teaching that I'll talk a little bit about in the next section that are these little, they're based on just a Raspberry Pi computer. So they don't have a whole lot of compute, but it was fast enough that we could run it with our, OK Python implementation on these Raspberry Pis and get the same behavior that we saw in simulation, even though we were using a fairly noisy localization model. We were just using a simple localization model that we use in the class, and they have a pretty noisy dynamics as well. But we were still able to we were really excited to see that this was able to work on the real robots too, and that we could use this, by solving these diverse solutions, we could get this adaptable behavior when the environment is dynamic. So that brings me to the end of the second section that I wanted to talk to you about, and to the last section where I wanted to tell you a bit about the work that we've been doing on robotics education. So I had the opportunity to develop a course as part of the robotics undergrad degree. We call it Hello Robot, Intro to AI and Programming, or Rob 102. What we call it here at Michigan. Michigan likes to use numbers only to talk about courses. And so basically the growth of of robotics as a field means that we need to develop new robotics and AI curricula that can scale across different universities and different diverse groups. So we're kind of seeing right now that enrollment in computer science nationwide is very high. There's really high demand for these types of programs. This is just the number of students enrolled in computer science at the University of Michigan, maybe the students who apply to computer science at the University of Michigan, even higher. And we're also seeing that the field of robotics is growing more and more. So this is the number of papers that there were presented at ICRA, which is one of our flagship conferences in the 20 years that it's existed. So robotics is getting more and more popular, more and more sophisticated, and that means more robotics jobs. And that means that there is an immediate need to develop new robotics curricula in higher education. And robotics has been used inside of computer science education specifically for a long time, for decades, especially to teach introductory programming. So there's a rich history of using robotics as a tool to kind of get students to visualize their programming, the programming concepts that they're learning. And so in terms of teaching robotics itself as a topic, this has also been being done in higher education in universities for decades. Since the 90s, there have been courses in robotics that are normally a special topic course or a graduate level course within some other department. And there's also, especially in the past, about a decade, there have been a growing number of robotics graduate programs, so more and more graduate courses in robotics getting offered where we can implement the actual algorithms that are of interest to roboticists. But at Michigan in 2022, we started a new robotics undergraduate degree. And that raises the question of what it looks like to teach robotics as a discipline, so throughout the undergraduate curriculum. And so we call this, we call our course a Rob 1 course. So what does it look like to teach a first-year robotics course that's meant for future roboticists? So our course, Hello Robot, in the first few weeks of the class, students are able to program the robot to move autonomously. So this is kind of our aha moment where the students get excited about getting the robot to move and follow them around. And then we get to do, in the beginning of the course, we're mostly working on learning programming skills, a lot like what the other CS1 classes with robotics has done before us. And we do projects like wall following with feedback control loops and bug navigation, where the students can have their robots go to some desired goal position. And then in the second half of the class, we start to think about more interesting algorithms in robotics that we might find on a real robot, like path planning algorithms to solve a maze, and image classification to detect handwriting and drive around in response to that. So if we want to be able to do all these things, this poses a really interesting educational challenge, because we need our robots to be simple enough so that students within the first few weeks can start to code and implement real algorithms on the robot. But then we also want to be able to do these interesting path finding types of algorithms. And so we had to do a lot of work to develop tools and methods to do this more easily. Specifically, we took a robot, the MBot that we have here at Michigan that is normally used in graduate, had been designed for graduate education, and we used it to set it up for an undergraduate first year robotics course. And we used some kind of interesting tools, like we made a flexible API so that it was more suitable for undergraduates to use, but it also can extend up until the graduate level courses and bring students through their whole robotics undergrad degree. So another big challenge that we wanted to think about was we didn't want to just think about what we could do here at Michigan, but also how we could scale this more broadly to other institutions. Since there's demand all over the country for more of these courses that cover the AI and robotics concepts. And so we taught this course as part of what we call a distributed teaching collaborative, where we were collaborating with other institutions to teach this course, and all the materials are available online. And so by collaborating with these other institutions, we lower the burden for these each school to individually build up their own curriculum in parallel. And then we can also improve and customize this course so that it benefits all of the instructors across all the different institutions. So we have a number of partners who taught this course with us over the past few years. We taught it at Michigan from 2021 until now. And the pilot offering was also offered at Berea College. This is a video of their MBot setup day at Berea College just this past fall, and we taught it at Howard University and Morehouse College as well. So it's really interesting to see how we could kind of scale robotics and AI education using these very different institutions, and what the challenges and pain points were to make that happen. So in my last chapter of my dissertation, I have a number of takeaways that I have from this course, which is first that we need more technology in robotics to kind of keep up with the demand for education. So robots are really hard to use. That's why it's normally only offered at a graduate and senior undergraduate level. You need a lot of skills. And so we needed to think a lot about how we could introduce some tools to use robots so that robots are more accessible to use. And this is really similar to the early computer science education, where computers used to also be really hard to program, and we've had increasingly more tools available to help make it more accessible so that high school students and elementary school students are able to write code today. And as we continue to develop more robotics courses and the community starts to push forward these initiatives, we need to have we want to start to standardize a robotics curriculum. So we have one that we've proposed for a Rob 1 course, but having the whole community behind what the right prerequisites are and the right algorithms to cover will help us move these initiatives forward a lot. And collaborative development has also been really key for us. Each institution has brought a unique perspective about what types of things are needed in order to get a course with real robots up and running. And so that's been working with diverse groups helps us make sure that we can scale this beyond Michigan. And so that's the now that I've talked a bit about my ongoing work, I want to kind of conclude and talk a little bit more about what kind of ideas we can take from here and going forward. So I've talked about my work on robotic perception and robotic planning using distributed inference. And I've also told you a bit about how we've been developing intro robotics courses to help scale robotics education. And I want to go back to this question that I asked at the beginning about the inductive bias, what the best inductive bias is for robotics. So if you ask me in the future what I think the best inductive bias will be, I think it will have to do with uncertainty. And so some of the models that this dissertation considers is distributed inference and non-parametric models, and this idea that if we want to solve these complex problems, we need diverse solutions. So there's some interesting future work that can be done, for example, in using different hybrid models at the intersection of machine learning and inference to solve some of these problems, and which can have applications to robotics, but also to broader AI challenges as well. I also talk a bit about my work in perception and planning uncertainty separately. So we need to also figure out how we can scalably model perception and planning uncertainty together. And this will let us be able to do real world robotics challenges in these unstructured environments. So with that, I wanted to, now is the fun part of the talk, where I want to acknowledge, so I want to first acknowledge my the funding partners who supported all the work that I talked about today. And then I also want to acknowledge the people who helped me to get to this point. This is a long list. I will try not to go on forever before I let people ask questions. But first, to my advisor, Chad Jenkins, for your kindness and your support throughout this process. I really appreciate all the opportunities you've given me that let me grow and learn to prepare for the next stage of my career. I have these notes here so that I don't mess this up. So I want to thank my committee. So to Jesse, I am always in awe of your ability to excel in everything at once. You're an amazing lecturer, a world-class researcher, but I mostly look up to your leadership. I am so grateful for your constant support and advocacy that I will aspire to emulate for the rest of my career. To Fabio, and I just don't have to make eye contact with these two, it's easier. I met Fabio when I was working at NVIDIA, and I'm so grateful we've been able to keep working together. Every time we meet, I learn so much from Fabio. Even if I have just an hour of meeting time, it's packed with months worth of wisdom that I'm very grateful for. And to David actually started at the University of Michigan, I think just a few months after me. And he was very helpful and knowledgeable while I was working on, especially on my first project. His office was right by my lab. And I still think about many of the things you said in the class I took with you about reading and writing papers. There's many David Foey quotes that I repeat back to junior students to this day. And to Mark is a highly respected authority on computing education research and very busy and important, and it's not his job to teach young robotics PhD students how to teach. But I'm very grateful that you did it anyway. You're a wealth of information about computer science and about education, and I'm very grateful that you agreed to go on this journey of writing a not so conventional robotics or education thesis with us. I also want to thank a couple other collaborators who've been particularly helpful for me in this dissertation. So Tucker, who is my mentor at NVIDIA, who is always very patient with me as I learned how planning worked on this project that I had never worked on before, and is also always there when I need advice on anything from robotic manipulation to faculty job interviews, and I'm very, very grateful for that. And to Karthik, who I like to think I was his first PhD student before he was Professor Desing, and whose support was very, very important to my first couple of years of PhD. Also my teaching collaborators who agreed to go on this crazy journey with us of teaching this course, and for their insights and feedback and mentorship, especially to Jasmine Jones, who taught me so much about teaching, and to Peter, who let me mess with his robot and help me fix it when I broke it. And to all of the students and staff who worked on Rob 102, who played a vital role in getting this course off the ground, and whose enthusiasm and curiosity is an endless source of inspiration for me. To the staff of the robotics department, I am pretty sure that Michigan Robotics has the best staff in the world who know the answers to every single question, and I'm pretty sure hold collectively all of human knowledge. And I don't know what I'm going to do without them. I've missed a lot of them here. To my lab mates, past and present, whose support and feedback on my work has always been super valuable to me. I've been lucky to be part of such a great group of people. To all of my friends, my old friends and my new friends who I met here in Michigan, I guess not so new now, for keeping me grounded and sane and making it this journey worth it. To my extended family for being the kind of family who makes me want to make all my career goals revolve around wanting to live close to you. A special thank you to everybody who's listening on Zoom. I saw a lot of you before I started. And especially my lovely mother-in-law, Sharon, and my wedding planner / translator / aunt Zian, who drove all the way out here to be here. And especially thank you to my parents who've given me everything and been endlessly supportive of whatever I do. You are the best parents in the world. And to my baby sister, Natalia, who I am supposed to stop calling my baby sister, but I probably won't, maybe when she is the next Dr. Pavlasek, for letting me boss you into following the same career path as me so that we can go to conferences together. And to my husband, my cheerleader, my first and last editor on everything I ever write, even like emails, for all that you do for me. Unlike our wedding vows, I didn't even use ChatGPT for this, so I'll keep it, so I have to keep it short. But here's to many more adventures together with our sweet boy, Darcy, who, by the way, was not that much help with this thesis because of his fear of robots. But thank you to Darcy anyway for reminding me that there's more important things than work and motivating me to finish this thesis and get a real job to pay for all his anxiety drugs. And so finally, I want to mention that I'm dedicating my thesis to my granddad, Dr. Tom Pavlasek, who I think is on Zoom right now. My grandfather is McGill engineering class of 1944, who went on to be a professor at McGill, where he still holds an emeritus position. And growing up, I went through phases about what I wanted to be when I grew up, just like all kids, until I finally settled on electrical engineering, just like my granddad. But one thing that I never swayed on was that I wanted to be Dr. Pavlasek, just like he was when I grew up. So hopefully that'll happen, soon. But if I can manage to be half the Dr. Pavlasek that you are, I will count myself lucky. So with that, thank you so much for your attention and for being here and for listening. And I'm happy to take any questions.